I work at CERN in CERN IT. I will be talking today a bit about how we manage our infrastructure at CERN and a bit about the history of this infrastructure, and then look forward also to what's coming next and what's already happening now. I work in the CERN Cloud team. I focus mostly on Kubernetes and containers, but also networking and software-defined networking deployments. More recently, I've been focusing also on GPUs and other accelerators mostly for the purpose of machine learning workloads. In the Cloud Native Computing Foundation, I'm the representative of CERN in the end user community. I also joined the TOC, the Technical Oversight Committee, earlier this year, where we try to help with the ecosystem in the cloud native area. And I also lead the CNCF research user group. So that's a group dedicated to making sure that all this ecosystem works well for research workloads that we will see are a bit special if you compare to traditional IT workloads. So we thought it was a good thing to have a dedicated work group so that we get everyone together and also try to give feedback to the different projects. So a bit about CERN for those that don't know or don't know a lot about its details. So CERN is the European Laboratory for Particle Physics. It was founded in 1954, and its main purpose is fundamental science. And what that means is answering big questions like what is 96% of the universe made of? What's dark matter? What's dark energy? What was the state of the matter just after the Big Bang? There's something called the quark-gluon plasma that we try to understand a bit better. And why don't we see antimatter in the universe? We know that in theory, there should be the same amount of matter and antimatter, but we only see matter. So we try to investigate that as well. In reality, to answer these questions, we build very large scientific experiments. So this is a picture of the biggest one we have, which is the Large Hadron Collider. It's a particle physics accelerator, which is 27 kilometers in perimeter. It's 100 meters underground, and we accelerate protons, two beams of protons, one clockwise, one counterclockwise, to very close to the speed of light. And when they are stable, we make them collide at very specific points where we've built these very large experiments called CMS, ALICE, ATLAS, and LHCb. These are very large detectors where we try to see what happens in these collisions. To have an idea of the scale, you can see this is the CERN has two sites. This is the one in Meyrin, and this is the other one in Prevsa. And you can see the Geneva airport for a notion of the scale, and the Geneva Lake here on the right. So underneath, if you would go to the tunnel underground, we have the accelerator and its magnets in this case. So in the center, we would accelerate the proton beams. To get to these high energies, we actually have to cool down the accelerator quite a bit, to very close to the absolute zero, 1.4 Kelvin. And it's very often, we say it's the coolest place on Earth, and it's literally the coolest place on Earth. And then where we make these collisions, we have these very large detectors. These caverns are quite big. They can be, I think it's 40 meters by 40 meters. The detectors are huge. You can see a human here for the idea of the scale. This detector is the compact muon solenoid, the CMS detector. It weighs 14 tons. And the collisions happen in the center here, and the detector acts like a gigantic camera. It's not an actual camera, but it acts like one. Taking something like 40 million pictures a second. And this allows us to try to track the results of the different collisions to see what came out of them. In reality, these collisions generate, what we get from them is a huge amount of data. Each of these detectors will generate something like 1 petabyte of data every second. This is not something we can process. So what we do is we have this, what we call online filters that will already reduce the amount of data to something like 10 gigabytes a second, which we can handle after. And this is what we have to store and later analyze. So this is just a visualization of one of these events, just a 3D display. But the end result, at the end, all this work is towards building a plot. So this is a famous plot. This is the plot that showed the bump for the Higgs boson back in 2012 that gave the Nobel Prize in 2013. You can see in the plot, what you can see is like the blue parts are what we know from the standard model of physics. And then we have the red part, which is the proposed theory for a new particle in this case, for the Higgs boson in this energy range. And then the black dots are the actual data, the things we saw from the collisions in the detector. And after analyzing them, we can plot them. We need a lot of data to have the confidence level that we need to claim a discovery. But once we reach that, in this case, we could see the black dots following the theory, and we could claim the discovery here. We have a couple of other experiments on site as well. One of them is the antimatter factory. This is just down the road from CERN IT. We build antimatter to try to understand better its characteristics. And then another experiment is AMS. It's actually installed in the International Space Station. It was launched along the last mission of the space shuttle a few years ago already. And it's basically by being above the atmosphere, it can do better analysis of things like cosmic rays. I mentioned a lot of data. So in reality, we are storing all this gigabytes a second, which come up to a large amount of data. And this means that we need a lot of computing capacity to process and analyze that. So we've built what we have today is a very large private cloud based on OpenStack, and you can see that it's something like 300,000 cores. We have actually closer to 10,000 hypervisors today, more than 34,000 VMs, and even if you look at the number of projects and users, it's also quite impressive. So it's a quite for in terms of on-premises private deployments, it's a very large deployment. And this is what the talk will cover a bit, how we manage this type of infrastructure. Now, the fact is that even with this kind of deployment, we don't have enough capacity to process and analyze all this data. So over the last 20 years, or even a bit longer now, we've built a system called the grid, the LHC computing grid. And what this is a network of something like 200 sites spread around the world that are connected together with high-speed dedicated links between themselves, and that basically allow centers around the world, like universities or big research labs that have quite a bit of computing capacity, to share and to collaborate with us to offer it for the analysis of the LHC data. So this allows us to more than double the capacity. We are close to 1 million cores these days. The system has been in production since 2006, and it's really the core of the processing facility for the Large Hadron Collider data. What we try to offer here is a single centralized system where users from different experiments can submit their jobs, and the system will hide all the complexity of having this type of distributed infrastructure. So it took quite a long time to develop it in the early 2000s. And this is pre-cloud era, so we're kind of by ourselves with a couple of other scientific communities that also have similar requirements. But it's been in production and very efficient for quite a while now. So in total, we generate something like 70 petabytes a year with the current current accelerator and the experiments we have. Accumulated, we already have more than half an exabyte of data stored. Now, the big challenge is that if we look at actually not so long, if we look in the near future, there will be a big. You can see the amount of data required for the experiments, and you can see that it starts ramping up very quickly in just a couple of years because we will have an upgrade of the accelerator. It's called the high luminosity LHC, and it's high luminosity basically because it will generate a lot more data, a lot more collisions, a lot more data. Uh, so with this upgrade, we have to look at something like 10 times more data that we need to analyze. So we need to evolve the infrastructure to be able to process this while keeping a flat cost with no more resources. So it's always a challenge. It's not the first time we have to deal with this kind of ramp up. And that's why we keep looking at new technologies constantly. Now, going back in time to explain how things have been evolving and how we hope they will continue evolving. When every time we have this type of ramp up, we always hope for some breakthrough in terms of hardware or in terms of automation and deployment, or in terms of completely new concepts that can help with dealing with this sort of order of magnitude increase. If we look back in time, in the 1970s, this is the exact building of the current data center, but you can see that at the time it looked very different. It was more like a living area, a working area more, not really living area, but working area with desks and some closets. And then you can see on the back these mainframes. These were the main processing facilities for the data at the time. Um, when I joined as a student, now quite a while ago, that we still had one left. Not this one's, but a more recent one was still in the data center. And then the big transition that happened here is that from mainframes, there was a move to commodity hardware. And the first version of that type of installment looked very much commodity in the sense that we were just piling up desktop machines in racks. These are desktops that look very much like the ones you would buy at home, which were cheap, but they were actually very inefficient. So they didn't last very long in this type of layout in the data center. The power consumption and the cooling are quite inefficient. So it's not the best way to have a large amount of capacity deployed. But we did keep them for a couple of years. What you see here on the right are the tape um, systems. This is one characteristic at CERN that is sometimes surprising for people visiting, is that we still use magnetic tape, and this is our main backup. So all the data goes into tape. Um, we used to use it as the first replica, but actually now we use it for backup. And if you come here, you will see a lot of tape in the racks, in the closet, and then the robot picking them up on request. There are several reasons to use tape. One is that it's very cost effective because there doesn't require a lot of power, and it can store a large amount of data in a small space. And they are also very reliable. We have some tapes that are more than 30 years old that are still uh, usable. Now, of course, the transition to a more modern looking data center has happened a while ago. This is how pretty much how it looks today as well. We have this traditional row and rack deployment. One characteristic is because this building has been adapted over time, you can see some tricks done, like these acrylic panels on top of the rows that basically will block the cold air from going upwards and force it to go through the machines. The deployments are using typical blade servers that you would see in any modern data center these days. I will also mention a very special computer that we have on display here. This is the next machine that Tim Berners-Lee used for the first web server. So another thing that CERN is famous for in terms of computing is the creation of the World Wide Web by Tim Berners-Lee. This is the exact machine that he was using in his office as the first web server. There was then a second one in MIT across the ocean. There was also a sticker here that is quite funny, which said that this machine is a server, do not power it down. And this was his way of telling whoever would show up in the office, maybe to do some cleaning in the evening, from not unplugging it to plug a vacuum cleaner or something similar and make sure it's running. Otherwise, the web was down. This was back in '89 before it was given to the public domain in the early 90s. So a bit again, looking at the evolution of the infrastructure that we had, and in general, in fact. What I will try to do here is have in the columns some characteristics of the infrastructure and how they rate in these areas. And we'll start with the traditional physical infrastructure deployment. This means you would just deploy your workloads directly on physical machines. And if you think about physical machines, you can think that for example, provisioning of a physical machine can be quite long. If you ask for a new machine, you probably have to open a ticket. Then there will be someone that will do some manual operations, maybe to connect to the proper networks, to make sure that you get the right machine and that it's connected to the right network, and any kind of specific setup that you might need in the machine. And then finally, you get access to it, but also the installation of the system has to be done in some way. So I put here days. It could be weeks in some cases back in the times that this is all we had. Then the second item is maintenance. If there was an issue with the machine, say a faulty card, basically you have to bring the machine down, meaning that whatever workload is running there will be impacted. And so these operations are highly intrusive. The other point would be deployment. In this case, once you have access to the nodes, it's a very traditional like Linux or Windows node where you connect, you do your deployment. So maybe it will take minutes. In some cases, if you're using some configuration tool, maybe it takes a bit longer, a couple of hours, an hour or so maybe. And the same is for update. And then the last column, which is very important, is utilization. So if you're relying, all you can have is physical machines. This means that you're allocating full nodes to every single application. And even like applications that do not need a lot of capacity, it might be that all you have is large nodes and you end up allocating them. And it's not easy to share workloads in this way. So the utilization ends up being quite poor. So the big breakthrough came with the virtualization and then the cloud API. So I will start. The main one here is the mix of the two. So if you think of virtualization, it's the ability to isolate multiple machines in practice in the same physical box, running different kernels, so they are totally isolated. The user actually doesn't see necessarily that this is happening, and they don't see each other either in the same physical machine. But for provisioning, this is only half of the story. What we also need to improve provisioning is an API that allows us to interact with the system. So instead of having to open a ticket and having someone doing this for us, it's very important to have an API where you can create a server or destroy a server or create a storage volume, attach a sort of storage volume, this sort of operations that the cloud kind of brought with this notion of having this API-based interaction with the infrastructure. So this was a huge breakthrough in terms of provisioning. You could now get a new node provisioned in minutes instead of having to wait days. Then in terms of maintenance, I put here potentially less intrusive. There is the possibility, once you have this virtualized infrastructure, of what's called live migrating the virtual machines from one physical node to another physical node. If this is supported and possible, then the maintenance can be a lot less intrusive. You could evict the different machines from a physical node and move it to and empty it so that you can do the maintenance and then put it back online once that's done. This is not always possible, so that's why I say potentially less intrusive, but there's definitely the possibility of doing this, and we actually do this daily on a daily basis in our cloud. Deployment and update, you're still dealing with physical with machines, say Linux machines. In one case physical, the other case virtual, but actually the interaction with the machine is very similar. You probably will just SSH the box using root or some other account, and then the installation of the software and the management of the software is done in the same way. So in this case, it stays the same. And then the big jump here is also in the utilization. Suddenly you can have multiple workloads safely deployed in the same physical box, isolated, which means you can pack a lot more in the same amount of hardware, and the utilization obviously goes up. So for this type of infrastructure, if you're doing this on premises, you need some sort of software that can manage these cloud-based deployments. At CERN, we use something called OpenStack. I understood that there was a earlier talk from Jonathan about OpenStack as well. So we had it this deployment since 2013 in production, and it's been growing ever since. And it's now taking pretty much the whole deployment in our on-premises infrastructure. We deploy 3 different regions in the same on-premises deployment infrastructure. And this is for scalability. Actually, there are some components in the control plane that don't scale very well to the size of our infrastructure. So we actually split the deployment into multiple regions. And the main reason is to be able to scale independently, but also to do rolling upgrades. When we have to upgrade the underlying cloud software, it's always a very delicate operation, as we have production workloads there. So having multiple regions allows us to do it gradually and to do it in the less relevant regions first, and then slowly go to the more critical regions as we gain confidence with the upgrade. And then within the region, we also need to scale. So we split the deployments into something called cells. And these cells basically match hardware deliveries. So the way we do it is, imagine we buy 200 to 300 new physical servers. We pack them together. We do the network setup independently for that group of nodes, and then we put it in production as a group, as a new cell into the infrastructure. So it allows us to manage this as building blocks. It also allows us to have an heterogeneous infrastructure. So maybe you have different components running in different cells, and maybe you have different types of hardware. Maybe you have like Intel and others AMD, or in some cases you have only CPUs. In the other cases you have also GPUs. So this is a very nice way to split also the infrastructure. And then in terms of hypervisors, we use KVM. We used to have a mixed deployment with a Hyper-V as well, but for now, right now we moved to only KVM. So this is something that has been working really well for us, and it's in production for many years. This is the growth of the number of hypervisors. So you can see that we are close to 10,000. And this has been a mix of like starting slow and onboarding existing physical servers gradually, but also new arrivals. You can see these big bumps with the like large amounts of hardware arriving that were put directly into the OpenStack infrastructure. Feel free to ask any question. I'm happy to stop in the middle as well. This is a similar growth plot for the number of virtual machines. So we are close. We are actually passing the 30,000. This is an old plot, in fact. When you're managing this type of infrastructure, one thing that is critical is to automate everything. Once you start having tens of nodes, you probably start suffering if you're not doing full automation. If you're having thousands of nodes, you basically will never get away with it unless you really automate everything. And this means automating the setup of the infrastructure. So this means the control plane and also the hypervisors running the virtual machines. And we've been using a tool called Puppet to do configuration management across our infrastructure. But it's not only the configuration and the deployment of the nodes. We also need to automate the tasks that are required when you're running a large infrastructure like this. And this is things like onboarding new users, or creating new projects, managing quotas, or allowing special capabilities for different projects. If we have to handle this manually, then the size of the team will have to be much bigger. We have a small team managing the whole cloud infrastructure. So this means that with time, we've enabled these workflows that allow us to also automate all these processes. So this is critical when you're running a large infrastructure. And then the last bit is to make the best use of our cloud. We always have some spare capacity because there will be new requests coming, but we don't want to have that spare capacity idle. So we do things like backfilling with traditional batch data analysis workloads. So when servers are idle, we deploy instances that will just do data analysis, automated data analysis. These instances are what's called preemptible, meaning that if there are higher priority requests coming from end users, these instances will actually be killed, and the capacity will be reclaimed by higher priority users. The other part that is quite important is overcommit. So we mentioned that from physical to virtualized, we gained a lot by just having virtual machines in multiple virtual machines in the same physical box. This helps, but it's still, we have cases where the virtual machines are still, the claim for resources is still too high for the application running there, which would end up with underutilized physical resources. So in a lot of the, in one chunk of the infrastructure, what we do is we overcommit resources, meaning we advertise more than we actually have, more cores. And this allows us to deploy more virtual machines that share the cores between themselves. And if they are not all or a large fraction maximizing the usage to what they claim, then the system will work. And we kind of monitor when there's a workload that is actually needing what they claim at the top. And if there are too many in the same node, then we try to move them around to make space. But this has been working really well for us. Then around 2015, 16, we started looking at containers. Again, because we have this evolving requirements constantly, we are also constantly looking at new technologies. And the one that came up more recently is this idea of running workloads in containers instead of using machines. And this coming back to this column-based analysis, we can see that if you've used containers, the provisioning of a container or the deployment of container, it's actually in seconds. So we don't have this boot time anymore, a different kernel. So we can actually spawn these workloads really, really fast. This has a dramatic impact in terms of the management of the application. You can do large upgrades across a very large infrastructure in seconds, which kind of changes a bit the way we manage the application deployments. And then another thing that comes with containers, if you're using an orchestration engine like Kubernetes, is that you're actually not deploying the application, you're declaring how your application should look like. And this is in terms of the number of replicas that should be running, what type of affinity or anti-affinity you have between the replicas, and the association with other services that might be running in the same infrastructure as well. And what this allows is the orchestrator to make a much more informed decision in terms of where the workload should be running. So if you have 3 replicas running across availability zones, and you need some intervention in one of the availability zone, then the orchestrator can make a decision by itself. Okay, this area is down or will be down. I can cordon this and move the workloads to another area to keep the desired number of replicas up and running. So this is makes it less intrusive because you don't really need to know or announce the interventions to the end users. You can just trust that the orchestrator will do that job. And then deployment and update. This is also something that changed quite a lot. The deployment we just mentioned, because you don't have the kernel, is much faster, but also the update, the orchestrator will try to reconcile the desired state to the actual state, and it does this much faster than the traditional configuration management tools. And finally, utilization. So we had a big jump from physical to virtualized infrastructure. We have another jump, smaller, but another jump into containers. And the main reason here is that while with virtual machines, we're actually isolating using different kernels. In containers, we are isolating using kernel constructs like C groups or namespaces. And what this means is that we only run one kernel and we reclaim a lot of the memory that is being used if you have multiple kernels. So that's something that is very relevant when you have a very large infrastructure. If you're reclaiming just a couple of gigabytes here and there, if you have thousands of nodes, then you're reclaiming a lot of memory. So for these containerized deployments, we rely on Kubernetes mostly, or pretty much everywhere these days. It's became the lingua franca of the cloud. If you go to all the major public cloud providers, you will see that they have managed Kubernetes services offered, which means simplifies a lot your job. You don't have to manage the infrastructure. You just have to use the Kubernetes APIs and talk to the endpoints. Um, there are also other options if you're running an on-premises infrastructure like we do. In our case, we use OpenStack, so we rely on a tool called OpenStack Magnum, which is the tool that manages containers in OpenStack and container orchestrators. You have other options like OpenShift or Rancher or even kubeadm if you want to go lower level. This API allows us to abstract compute, storage, and networking and do this declaration of the requirements for each application. But actually, it's much more than that. It can manage any type of resource. So there are extensions and even built-in constructs to manage a lot more than just these basic constructs. So you can manage a database using Kubernetes. You can manage a Redis instance. There's a lot of like higher level constructs that allow you to rely on the control plane of Kubernetes to manage other tools. Now, the other big benefit is that with Kubernetes comes a lot of goodies in the ecosystem. So we are talking about deploying and manage the resources themselves, but actually when you're running a service, there are other points that are very important. For example, how you monitor your service, or how you collect the logs, or how you collect the metrics of your service. This is, if you would traditionally in our infrastructure, we would use Puppet to configure and then maybe use collectd or Flume to analyze logs and collect the metrics. In the Kubernetes world, this is kind of all connected in this cloud native ecosystem where the tools are built so that they can talk to themselves quite easily. So for example, for monitoring, there is a tool called Prometheus that also defines a way to expose the metrics. And most of the tools and the applications in this ecosystem will export those metrics in this format. And then there's a standard way for Prometheus to go and query them. So everything comes kind of built in, and you can expect them to integrate very well. And the same is true for logging. I put here FluentD. There's also FluentBit. But the way the logs are exposed from the containers and aggregated and then pushed centrally is also well defined. And there's a lot of other tools. So I mentioned here some, but if you go to this URL on the bottom, you can see the CNCF, the Cloud Native Computing Foundation landscape growing very fast. And yeah, any area you think of, you can go and find tools to try to help with that. There are different levels of maturity. The biggest being graduation, then you have incubation and also sandbox for entry-level projects. This is a nice way to also assess what's the state of the project if you are thinking of deploying it in your production infrastructure. So at CERN, we have more than 600 Kubernetes clusters running. 600 of them are Kubernetes. There's a couple of Docker Swarm clusters that are kind of legacy. We have a significant amount of nodes deployed. We have tens of thousands of cores running on Kubernetes. And we've seen that this is gradually increasing. We offer a nice way to have a Kubernetes endpoint so people are jumping in. Now, all this automation is very nice, and Kubernetes does a very good job about doing this. There's one area that is still needs attention, which is your actual configuration. So we were saying that your application definition is done in a declarative way, like it or not, in YAML files in the case of Kubernetes. This is a very nice way to describe how your application should look. But then there's the problem of managing the changes and the evolution of these configurations. Maybe you have multiple flavors of your deployment of the same application with different configurations. You need some way to manage this. You can do this just by keeping some files locally and pushing them manually. That works, but it's not the best way to do it. So one pattern that has been quite popular is this idea of doing GitOps, which is to version control the configuration data in the same way you version control your code, so that you can track the changes and the evolution of this configuration and the deployments. And then to have a tool that is running in the cluster that monitors this configuration, and whenever you do a change, it will pull the configuration and apply it locally in one or more clusters. You could have multiple clusters pulling the same configuration in case you want to spread the deployments. So this is very popular and a really nice way to manage large infrastructures. It's pretty much the way everyone is trying to manage the configurations these days. Other ways is to do a more like a push on some kind of CI/CD kind of deployment. But this idea of also having a tool that pulls also kind of abstracts the deployments, the details from the repository. You can kind of detangle them one from the other. So there are tools that are useful for this. One is Flux. The other one is Argo CD. They're both quite efficient at doing this kind of operation. One thing that is also important here is to, or relevant, is to decide how you want to deploy your application. So the most popular, at least at start, way of deploying is you create one cluster, you deploy your application there, and that's it. This works. You probably need to have some sort of high availability in the cluster so that you guarantee your application is always running, both for the control plane and also the distribution of the nodes across availability zones. The second option would be to have the same application deployed in multiple clusters. This will cover for problems with the clusters themselves. If clusters go down the control plane, your application might become inaccessible. So if you're doing multiple deployments, you kind of cover for that, and you cover for like an improved blast radius. It also allows you to do rolling upgrades. If you're upgrading the cluster itself, it's always a very delicate operation that might break. So you can do this cluster by cluster, and kind of maybe if it goes wrong, you get a degraded service, but it stays up. So this is also something to think about. There's this notion of having clusters as cattle. The same way we had VMs as cattle at the same time, to kind of have multiple instances, and if they are killed, your system can recover from it. There's this idea of having the same for full clusters that allow you to, for example, drop a cluster and deploy a new one, and the application will just spread in the new resources like this. And ideally, you would have multiple applications in multiple clusters. This is something like if you're managing OpenShift deployment, for example, this is the default. There are some more implications here. You have to have very well-defined role-based access control if you want to run multiple applications and multi-tenant workloads in the same cluster. It's a bit trickier, but it gives you a much better resource utilization. And the last part of the talk, I've been talking mostly about on-premises deployments. What I will talk about is, again, in this goal of always making the best out of the available technology. One big thing that came in the last few years is the availability of public clouds that give you this theoretically infinite capacity, on-demand capacity, where you can go get it and pay as long as you use it, and then destroy when you no longer need it, which is very tempting for a lot of use cases. The first one would be, for example, at CERN, we have periodic load spikes in the demand for capacity. So imagine we have a conference coming up, and the physicists want to do a lot of extra data analysis, and then they need extra capacity. If we would provision our infrastructure to those spikes, we would probably, for most of the time, underutilize our infrastructure, and that would be a waste. So ideally, we should provision for the normal usage, and then try to go and fetch extra capacity externally, and pay only for those periods where we need it. The same is true for things like GPUs. Machine learning has been growing a lot in usage at CERN. And we don't have a lot of GPUs on premises yet. So it's very tempting to go to the public clouds to get this extra capacity in accelerators, GPUs in this case. But also, if you're doing machine learning, and especially deep learning, there are dedicated accelerators for that, things like TPUs in Google Cloud or IPUs that are available via Azure. And these are dedicated accelerators that we might never be able to have them on premises, and we might need to go to the public clouds to make use of them. So this is another motivation. And then the final one I mentioned here, for example, if we buy a new set of GPUs, you probably want to buy the best model for the types of workloads you're planning to run there. So to get, it's very nice to go to public clouds and get a preview of all the nice new hardware that is available, test it there, and then we can make a much better decision of what we should buy in-house. The same is true for ARM, for example. There's some demand for ARM resources on premises that we don't have, but we can already start building packages for ARM by just using public cloud resources. So to validate this idea that the public cloud is useful, back in 2019, we decided to attempt to validate this idea that we could have a very large amount of resources for a short period, pay only for that, and then get rid of it and move on. For that, for a conference, KubeCon in 2019, we had a keynote where we had 20 minutes for the whole session. And we wanted to do a live demo where we would rediscover the Higgs that was the same analysis that was done in 2012, to do it in a very short period that we could show it live during the keynote session. So the idea would be to take the 70 terabyte data set from the Higgs that had the Higgs events, and then process it with enough capacity that it can be done in 5 minutes. The data set is 25,000 files. The software is quite old, but it was only single core, which meant we could have maximum 25,000 cores in the cluster, and then deploy 25 independent jobs, 25,000 independent jobs, each processing an individual file in parallel. This would allow us to maybe do it in this short time. So what we did, we started by deploying this on premises at CERN, and we were using the CERN S3 infrastructure, the Kubernetes infrastructure that I just mentioned earlier. But we had an issue, which is we didn't have the 25,000 cores for the demo because we have a production infrastructure, and no one would give us 25,000 cores just to do a demo. So we managed to do it with a lower number of cores, which allowed us to validate this deployment, and we did it in something like 8 hours. But what is important here is that we based everything using Kubernetes and the Kubernetes API. And what we did then, we deployed a cluster in the Google Cloud, and we have a collaboration with the Google Cloud via CERN Open Lab. And this allowed us to just point the same deployment to the Google Cloud, and then run the same demo there, but with a much larger cluster. So in the end, it worked out. We actually reached a pretty impressive data throughput from Google Cloud Storage, 200 gigabytes a second, multi-terabits a second. That was quite nice. Just very quickly, this is the cluster creation, takes 5 minutes for a 25,000 core cluster. The image pre-pool is a quite large container image, so that's why it's so slow. But the actual demo was these 2 steps where we'll pull the data and then process the data, and this took just over 5 minutes. And this is just a view of it. We were building the plot, the same one we saw initially in the talk. We were building it live as the data was being analyzed. I will finish just with machine learning workloads. This is where the public cloud has been really relevant. One big thing is that physicists are not necessarily computing or infrastructure experts. So they will be very good at getting stuff done, but maybe for machine learning, they will have one node with one GPU or a couple of GPUs, and these GPUs will be spread. So they will be underutilized, and even if people would like to scale further, they would be very limited if their workloads can only run in one node. So having this kind of distributed infrastructure for machine learning is also very tempting, and offering a centralized service for machine learning was also very tempting. There is a big difference from the traditional hyperworkloads. I mentioned that we had the Higgs dataset, 25,000 files, and we can actually process them totally independent. So we call this embarrassingly parallel. You can deploy jobs in parallel, and they don't have to talk to each other to get the results. But for machine learning, this is not always the case. Very often during the training, you need more communication between the different jobs. So we've been looking at a platform called Kubeflow, which runs on top of Kubernetes. And this is really trying to answer all the needs we have, which is to manage the distributed training, to manage the infrastructure and the deployment of the workloads and the coordination between the workloads. And this would allow us to do distributed training at scale with tens, hundreds, thousands of GPUs even. It supports all the popular machine learning frameworks. And it also offers additional functionality for things like notebooks for iteration when you're playing with your training initially. Um, and then it also serves the models. And one thing that is very important is this hyperparameter tuning. If you've tried this, you know that this is time consuming and very resource intensive. So it automates this process as well. So we've been looking at using public clouds for this because we need a large amount of GPUs. Eventually, we'll also have this capacity on premises. So here I would like to highlight that it's very important to be flexible. For us, at least, it's very important to be flexible in how we can use the public clouds. And again, the Kubernetes API is a big plus here. So the idea is that the CERN services can burst to different public clouds, supporting all the public clouds via the Kubernetes API. And even within one public cloud, being able to easily use multiple regions. The reason for that is that capacity can vary from one region to the other. So it's very nice to be flexible in this way. And just as an example, so if we take one example, which is 3D GANs for fast simulation. So to generate simulation data, we are also looking at using machine learning. And initially, one epoch of this training would take 3,500 seconds. And using the public cloud and this infrastructure based on Kubernetes and Kubeflow, we actually managed to scale this to using 128 GPUs in parallel. And we got almost linear scale. So we got 100 times improvement. And this is the sort of breakthrough we need to be able to deal with the increase of data that is coming up. This is a very, very interesting result. We also did, so you can see here the evolution of the scale with the number of GPUs. The other interesting result is the usage of TPUs and dedicated accelerators. You can see that we get similar results in terms of TPUs, for example, TPU V3 with 32 cores to get a similar result as the GPUs, as 32 GPUs. Now, the big thing about TPUs and that makes them interesting is that they are much more cost effective than GPUs. One thing that I would highlight is that because this workload linearly scales, actually we can scale and get 100 times improvement while spending the same amount of money. So this is really a big plus, is to optimize the training so that you can get close to this sort of scaling so that it remains cost effective to do it with a much larger amount of resources. And then the second thing is that if you look at the TPU costs, they are really at like 2.5 times cheaper than GPUs, which makes it really interesting as a potential future resource to use at scale. So I come to the conclusions. I would highlight, I think it was clear that this type of experiments and at CERN and elsewhere, they generate a large amount of data, which implies that we need a lot of computing power to process this. And what is sure is that these numbers will never stop increasing. We will have a 10 times bump very soon. We can trust that in 10, 20 years, the same will happen again. The big change that happened from, say, 20 years ago is that we used to be by ourselves, this type of scientific experiments, and no one else had this sort of scale in terms of the amount of data. This is no longer true. There's a lot of companies in the industry area that have similar or much higher requirements. And this triggered the creation of these open source communities that try to collaborate to build infrastructure tools that can scale to this size. And this is a huge change for us, because instead of having to build our own tools in-house, we are now collaborating with these communities and trying to help with the development, but also validating our use case. And this makes it much better for us, because we can focus more on the higher level parts than just having to focus on the lower layers. And these communities are very vibrant and active, so it's also very exciting to collaborate. And then the third thing is that it's quite important to stay flexible, to not lock to a particular technology. We need to be able to transition as new technologies and new types of software to manage infrastructure at scale show up. We need to be agile enough to transition to these new ones, so that we don't lose the train, and we can keep up with the demands from our physicists. And that's all I have.